Section 2.3 is all about continuity. Continuity is the state of being continuous. And it turns out for most functions in calculus, calculus won't work unless we can guarantee first that the function is continuous. So informally continuous means what you think it means. A function is continuous if you can draw it without picking up your pencil. It doesn't have any places, holes where it skips, or big jumps or gaps. But formally, we want to define continuity formally. A function is continuous if its limit from the left equals its limit from its right, and that limit equals the actual function value. So this is how we say here, you can see this is the notation you expected to know. F of x is continuous at x equals c if the limit as x approaches c of f of x equals f of c. So I'm going to hide me for a second so you can see the rest of the slide. This is the function we saw at the end of 2.1. This function is discontinuous at x equals 1. You can see there's a gap here. We couldn't draw that piece of the function without picking up our pencil. This function is also discontinuous at x equals 2. You see there's that hole I have to skip over. So the function is continuous for all other points of its domain. So I use bracket notation because this is a closed interval, x equals 0 to x equals 4. The function is continuous everywhere except x equals 1 and 2. Now the endpoints, so at x equals 0, this function is continuous because, remember, it doesn't make sense to talk about the limit of f of x as x approaches 0 from the left because x can't approach 0 from the left. So even though I only have a limit from one side, we can still say this function is continuous because it's continuous for every point on its domain. There are two main categories of discontinuities. The first is a removable discontinuity. If there's a discontinuity that just has a hole, where the hole is colored in somewhere else or not, if you could fix the discontinuity by filling in one point on your graph, it's called a removable discontinuity. The essential discontinuities are jump discontinuities, infinite discontinuities, and oscillating discontinuities. This oscillating type, it's the kind we talked about back in 2.1 that doesn't really happen very often at all, and it's not going to happen in calculus A, B, or BC. So there's a place for you to draw each of these, or to label each of these kinds in your notes. This is an example from your paper. We want to choose C so that this function f of x is continuous. There we go. So f of x is a piecewise function, x plus 3 as x approaches 2 from the left. So that's for all x is less than or equal to 2. And cx plus 6 for x is greater than 2. So remember our definition of continuity. F of x is continuous at x equals 2 if the limit of f of x from the left of 2 equals the limit of f of x from the right of 2 equals the actual function value at 2. So that's what I've written here. It's a three-way inequality. All three of these things have to be equal. So as x approaches 2 from the left, it's this piece of the piecewise function that's in charge, that's turned on. So that's what I have here, x plus 3. So I want x plus 3, when x is 2, to equal the limit as x approaches 2 from the right. That's going to be the second piece of the piecewise function. So cx plus 6, when x equals 2. And that has to equal what I already know is f of 2 because I can plug 2 into this function. The top piece is in charge, and I get 5. So when I plug in 2 for x here, I get 5. So 5 is going to have to equal c times 2 plus 6, which is going to have to equal 5. So I write 2c plus 6 equals 5. I solve, I get c equals negative 1/2. So choosing c equals negative 1/2 makes the function f of x continuous.